In this lesson, we are talking about universal approximation theorems which enables approximating any function using a neural network under certain conditions. Universal approximation has been proved in different theorems under different conditions. So it is not a single theory. Before going to details of universal approximation theorems, let's take some other examples where we approximate a given function using a set of other functions. The Fourier series combines sinusoidal functions with different frequencies in different weights to represent a given function. The weights can be found analytically using Fourier transform. In the Taylor series, a function can be expanded around a given differentiable point of the function. In a neural network, the approximation is slightly different from previous examples. Here we use a single function like the logistic function as the fundamental unit and combine them in different proportions to approximate a given function. In one of the earliest proofs of universal approximation theorem, Seibenko showed that it is possible to approximate any function using any sigmoidal function. A function becomes sigmoidal if it approaches 1 when x approaches positive infinity and 0 when x approaches negative infinity. Later on, Honig generalized Seibenko's theorem and showed that any activation function which is bounded, that is not a constant value, can be used to approximate a given function in a neural network. Bounded means the function should not approach infinity in either direction of x-axis. The main contribution of this theorem is proving it is possible to use functions other than sigmoids in the approximation. It is the feed-forward architecture of the neural networks that enable the universal approximation. Main restriction of those theorems so far is being limited to a single layer with a sufficiently large width. Sauve and later Patrick showed that it is possible to build universal approximators by increasing the depth of the neural network with narrow hidden layers. The main disadvantage of sigmoid functions when increasing the network depth is the vanishing gradient problem. ReLU, on the other hand, suffers less from this issue. It has a better gradient propagation through the network. Also, the activation is sparse as it doesn't produce a response for negative inputs. And the computation is efficient as the gradient is just a constant. Initially, it may be a bit harder to see how a set of linear-looking functions like ReLU can be used to approximate any arbitrary function. Let's try to understand how it works with an example. Here we have two ReLU functions. The function in red color has been shifted and inverted. When these two functions are combined, the resultant would be a function like the one shown in yellow. This resulting function looks similar to a sigmoid. Likewise, by combining a set of ReLU functions, we can approximate any given function.